everyone. Thanks for joining. My name is Atefeh, and I am an associate machine learning scientist at AMII. And today I'm going to talk about computer vision in healthcare. So this is the agenda that we are going through. First, I'll give a quick introduction and some high-level objectives. And then I'll talk about some computer vision tasks and following applications. And finally, we have the challenges and the future of computer vision. All right. So let's just start with the main question: why computer vision matters in healthcare? As you may all know, healthcare is a critical sector because it literally could be a matter of life and death. So the ability of computer vision to digest a huge amount of data, make sense of them, and spot patterns. So give us enough reasons that how it can help in this field. So you can see some objectives here. First is computer vision can help, improving diagnostic and treatment effectiveness. A large caseload and lack of medical history sometimes may increase the possibilities for human errors, and computer vision can help doctors to detect and diagnose diseases more quickly, more accurate, and with fewer errors. Next is fast and easy information analysis. So computer vision can analyze a large number of images quickly, and this is so helpful to ease medical procedures and also make them accurate. Next is fewer accidents and safer surgeries. So computer vision can help medical facilities monitor safety to reduce accidents and injuries, and also it can help doctors to perform less invasive surgical procedures. Next is computer vision can reduce the total cost of healthcare by reducing the need for manual expensive procedures and labor works. Also, patients will receive more accurate and faster care, so it also reduces the need for hospital admissions and insurance costs. And finally, computer vision accelerates healthcare research for new diseases and pandemics like COVID-19. Already. So let's see, what is computer vision? So it's simply a sub-branch of artificial intelligence and machine learning, and it means the study of visual data. And we have different types of medical images, like X-ray, CT, MR, and so on. So computer vision can help, definitely help. So it's usually used with high-tech cameras and sensors to extract and visualize information in a way that they are useful for a variety of applications. In the right, you can see a simple comparison between human vision and computer vision. In this example, let's say that the doctor looks into the patient's chest radiograph, and then the brain interprets it as a lung cancer. In the other way around, computer vision does the analysis to conclude it as a lung cancer. But compared to human vision, it may only take a few seconds to conclude it. But it's not as simple as it looks. So there are lots of challenges in this field, and that's why AI and computer vision, they are all used as doctor's assistant, not doctors. All right, so let's move to the main computer vision task and start with the object recognition, which is a hard for variety of applications in healthcare. So usually object recognition includes three main tasks. The first one is object segmentation, which means grouping grouping pixels to meaningful area. As you can see here, there is the abdomen CT example, and automatic segmentation delineates organ area. For example, you can see the segmentation of liver, kidney, pancreas, and spleen here. All right. Next task is object detection, which means putting bounding box around objects to show where the objects are in the image. As an example, you can see a thyroid ultrasound image with a detected nodule in the isthmus area here. All right. Next is object classification, which means each object belongs to each category. Here you can see two skin lesion images with classification results. One is highly possible to be malignant, and the other one is highly benign. Already. But computer vision is going beyond object recognition in healthcare. For example, image registration, which means systematically putting separate images into a common form of reference. So the information they contain can optimally integrated or compared. And as an example, you can see a brain tumor registration here. Next is image reconstruction, which as its name shows, it means obtaining high quality images so having a more constructive and useful image for the human observer. So there are two forms of image reconstruction, one 2D and one 3D. As a 2D example, you can see removing aliasing from MRI brain. And for the 3D one, I put 3D reconstruction of knee from X-ray images. All right. Next is denoising and enhancement, which is an essential pre-processing step for many applications. And you can see a chest CT denoising as an example. Next is generating synthetic data, which is super helpful, especially for data-driven and deep learning models, because of lack of medical data and, skewed class distribution. In many medical areas, there is a need for some synthetic, highly realistic images to use. So as an example, you can see a synthetic skin lesions compared to the real ones. All right. So let's move on to some popular application and start with pharmacy automation. So computer vision can help in automating the prescription ordering. So basically, it can use OCR to extract information from prescription image. Next is computer vision can help doctors to detect and diagnose tumors and cancers. Usually, computer vision models are trained through machine learning and deep learning with the data of cancerous and healthy tissues, let's say. And yeah, it can help to make the process more accurate. Next is one of the most common and popular one, which is better image analysis. So as I already mentioned, so the computer vision ability to recognize patterns, it helps doctors to detect and also in the process of treatment, also it can help a lot. Next is surgical guidance. Computer vision is used to guide surgeon doctors during the surgical procedures by using the cameras enabled by machine vision, and also by improving and developing, surgeon robots these days. The surgical procedure would be less, tiring and more accurate for doctors. Next is reduce patient mix-ups. Patient misidentification is a common issue in healthcare, and it can, result very dangerous consequences for both patient and also the healthcare provider. So computer vision face recognition can help in this situation. Basically, accessing to personal information by face recognition can also improve the privacy and also, control systems. Next is workplace safety. So computer vision can help, establish for the potential incidents and, alert relevant authorities when needed. Also, computer vision, the surveillance system can track if staff use appropriate equipment and procedures. Next is smart operating facilities. Computer vision can automate the recording process of surgical procedures that may involve repetitive and error-prone tasks. And also sometimes surgeons forget surgical instruments inside the patient's body, so computer vision can track the surgical instruments for avoiding this issue. And finally, computer vision can help in investigation and testing in new treatments. For example, a computer vision system can do more accurate and less biased cell counting compared to human workers. All right, so let's talk about the challenges in this field, and start with the most common one, which are data-related challenges. First is finding, high-quality images is always a tricky part, especially for using computer vision and machine learning models. Basically, during the acquisition of medical images, they usually suffer from one or more issues. For example, low contrast, low resolution, high level of noise, geometric distortion, and these type of things. And also the sensitivity nature of medical images makes it more difficult to collect. And even if we collect, we need to make sure the data is valid, reliable, and accurate. So it comes to the next challenge, which is data annotation and cleaning. So sometimes more than 10,000 images are required for training a computer vision model. So it could be very time-consuming and more expensive, even when automated. And you know what? The annotation process is different from annotating non-medical images because only an expert has the knowledge to do that. And also, even between experts, sometimes they don't agree each other about a label. So it could be super confusing and make a bias and error in the data. Next challenge is data drift, which is because data is generated in a non-stationary environment with shifting patients' populations. And also there are differences between sites in terms of technical equipments. For example, different hospitals may use different lab equipment or assays or code definition. So this also results a shifting distribution in the data, which reduces reliability. Next challenge is lack of metadata. So usually databases are not complete in terms of fully tracking all the patients' pathways, and it may increase the inconsistency in the data. And finally, data privacy and availability, which is a very prominent concern, especially when it comes to the healthcare industry. Usually, patients' data includes sensitive information, for example, medical histories, identity information, payment information, and these sort of things. Privacy-enhancing technology must be taken to avoid data leakage. There are also other challenges in this field. For example, the highly negative impact of false predictions, which may lead a very serious situation. Next challenge is related to metrics. So metrics don't often reflect clinical applicability. For example, accuracy doesn't necessarily clinical efficiency. And also sometimes a metric is not completely understandable by many doctors or clinicians. Next challenge is accidentally fitting confounders versus true signal. So highlighting unknown confounders by computer vision models may increase the generalizability issue. So from my experience, for example, my model was more likely to detect and classify a thyroid nodule as malignant when the input data included a ruler inside the image. And it was only because in my training data set, most of the cancerous cases included ruler in them. Next is lack of interpretability and trust. In the healthcare setting, there is a demand for models that they are not only well-performing, but also they are, explainable, transparent, and trustworthy. So, although the current models are perfect and have shown that impressive results, but they are not still able to completely, explain the decisions in a more understandable way, please. All right. So as you know, the challenges, you may guess the future. Let's start with taking a human-centered approach. So as Feifei says, it's a key to advancing state-of-the-art of computer vision in healthcare, which means shadowing, doctors or nurses how they detect and diagnose the process. Well, it's a key to successful adoption of AI-based solutions. Another thing is just overcoming data challenges, as I mentioned, identifying and reducing unintentional biases and unfairness, improving generalizability, identifying data drift proactively and updating models, improving interpretability and explainability, and developing reliable metrics. So the takeaway messages are computer vision, AI, machine learning, deep learning, they are all very life-changing. And they are making the world to a better place for humans. And AI won't replace doctors, and the applications are not a threat to doctors. Exactly opposite. They're trying to help them to enhance the quality of clinical decision making. And the last one is doctors who use AI, especially in the future, will definitely replace with those who don't. Thank you. Yeah, thank you.
I actually was a graduate student a couple of months ago, and I was working with medical image segmentation. Yeah, I did thorax CT segmentation, so it was interesting. One thing I'd like to ask from your experience is, I also went through a couple of the challenges that you mentioned. Yeah, so I had a bit of a problem with metrics, especially explaining my metrics, which were F1 score, to the radiation oncologists that I was working with. So for that, from your experience, have you changed your metrics? Have you used new metrics for image segmentation? And how do you communicate them to the medical expert? Do you have any insights on that?
Yeah, for sure. So for the F1 score is usually for detection, not for segmentation. And it's a trade-off, It depends that you are more caring about false positives or false negatives. So for example, if you want to not missing anything in the image and you want to detect all, so basically you're more taking about false negative. So you want more recall than more precision. So you may just change the metric in a way that you are weighting more on recall. not on the precision. And for segmentation, usually, for example, using the intersection, the boundaries and the intersectional area.
Hausdorff distance and stuff, that's
Yeah.
what we implemented as well. Hausdorff distance and other segmentation so that we get more information about the overlap.
Exactly.
IUU and stuff.
Yeah.
We use those as well to explain like how better it is. But again, so the follow-up question, how did you communicate stuff like Hausdorff or IUU to the medical expert?
So based on my experience, usually if you're working with doctors or radiologists, these are the best way to, confirm with them, this is what you are, what exactly that you are looking for, what do you think? And then based on the feedback that you are, getting from them, you can just, basically you have a couple of metrics and you can decision which one is better and you can more weight on that. Does that make sense?
Just like discuss them, and definitely we will give a lot of qualitative results as well, but again, if the data set is large, how many can you print?
Yeah, another thing, right. So you do have the quantitative and qualitative result, which should be consistent to each other. For example, sometimes the metric, for example, say that, as I said, the accuracy is high, but it doesn't show in the visual results. So there is something wrong, for sure. Yeah.
Also, is there a difference in your data set or your experience as well compared to if there's a non-medical data set? Because from my experience, the same metric is just lower, like the baseline is lower, so your improvement of even a 3% is low. But whereas if the same thing going on with a different data set, like
for sure.
Human detection, they're getting
exactly
98%
for sure.
Or so.
Yeah. It will increase. Yeah. So yeah, it's different. It's just different. But usually they are using the same metric. But yeah, you need to confirm that this is exactly what you want.
And sorry, I have a lot of questions. Is that okay? We have a question. It's just it's true. Like 2 medical experts might not agree that this is a tumor. Yeah. How did you solve that problem?
Well, we use kappa score. Kappa score usually shows you that how much is the agreement between experts. For example, you're giving your data set to maybe challenging data that you have to 2 radiologists or 2 doctors to label them, and then based on the results, so they don't know that the other person labeled. So based on the kappa score, for example, you are ending up with something less than 0.5%. So which means that even the agreement between doctors is not high, which means that so the model, if the human cannot end up with the same result, so how we can expect the model to do that? So it somehow shows that it's not something wrong about your model. It's just
Thank you so much for your talk. It was amazing. So you talked about how some of the challenges with computer vision is data related, and you talked about the application of AI in that. And I was just wondering, would there be something in blockchain or using quantum computers in detecting things like cancer in patients?
I would say I don't know. So I don't have the experience in using blockchain and medical in the same,
Yeah, like
these are different.
or at least even for AI, like getting that data synthesis. What kind of process is that involved in?
For synthetic data, usually it's better for non-medical tasks because it's not that much critical rate medical ones. For example, as I showed, the lesion skins, for example, you can generate some, but you need to confirm that these are consistent with those that real ones. But in non-medical way, you can generate. Let's say the data, and it's not that much BB generative models, for example, you cannot, it's not necessarily that much critical to, having something exactly, realistic looking like medical images. Did I answer your question?
Sorry, I think this one should be the last question.
I had a question on
the data drift that you mentioned.
Right.
How do you measure that quantitatively in your applications, and what do you actually do with the models once you realize the data drifted too far?
Mm-hmm.
And what happens to those predictions that were happening during the data drift?
Right. Well, it depends. One thing that we can do is just fine-tuning the model for the new distribution. For example, you have the model, but it really depends on how many data you have for the new case, for the new, let's say, population, and then you can just, based on that, decide about how to, shifting the decision of your models.
Since your decisions are so critical, like you said, it's a life and death question.
Right.
What happens to those people that were predicted
Exactly.
at the stage of the data drift?
Yeah, so the challenges would be, I would say that these are some open challenges as well, that we can do something, but every step that we take, we need to confirm that this is reflecting in the results. So yeah, you're right, so the challenge in medical is much more serious, so yeah, you need to confirm. Okay, thank you.